So let's see. The important part is that if you find your ion in the ionic compound on the left side, it will be aqueous. If you find it on the right side of the solubility rules, it will be solid. I can't show all of these on here at once, but we want to basically write whether it's solid or aqueous for each compound. So we looked at aluminum, and we saw, I'm going to use this one so that I can see it, even though it's not on screen. So as I go down, I don't see anything from rule number 1. I don't see anything from rule number 2. I have aluminum and chloride. So I get to chloride in rule number 3, and aluminum is not listed as an exception, and that means that this will be aqueous. So I'm going to write that designation as aqueous. Now what I'd like you to do is go through all of these and write solid or aqueous on each one. Okay, what did you get for B? Lithium chromate. For B, I get aqueous because lithium is in rule number 1. Chromate comes in rule number 6. It's later, so rule number 1 is more important. For lead 2 bromide, so we can practice naming, you could say that out loud. It's probably good to hear it as well. So lead 2 bromide will be a solid. Bromide comes in rule number 3, but the lead is an exception to rule number 3, making it solid. So make sure that you are checking your answers. And if you get something different, let me know. Let's figure out why. I added one in down here that's a little bit extra challenging. F, silver phosphate. Yeah, so here's our phosphate. So it's a solid. Now we do see silver here as an exception. Silver also makes halogens solid. So silver chloride, silver bromide would be solid. Aluminum chloride, aluminum bromide are aqueous. So both of those ions give us a solid. But really, it's the phosphate. It's really the phosphate rule that tells us for F.
C, can you go over C?
C, yeah, so rule number 3 gives us the halogens, the bromides. So here's our halogen rule. We have a bromide, but it's paired with lead. Lead is an exception that makes it solid. All right, barium sulfide is another tricky one. Well, let's look at I. Let's look at K2S. In the sulfide rule number 9, it would be solid, but we reach potassium first. So potassium wins, that's aqueous. Now for this one, for barium sulfide, we get all the way down to the sulfide rule number 9. And then we see our exceptions. These exceptions are aqueous. They're on the solid side of our table, so the exceptions become aqueous. Sulfide ion is solid, right? But barium sulfide is soluble, so that means that it's aqueous. Rule number 9 means that sulfides are solid unless they're paired with calcium, strontium, or barium. So here's what we're going to see. If you look on the periodic table, look at these ions over here. There's that little Tetris shape if you've played the game Tetris. So here we have lithium, sodium, and potassium. And then here we have calcium, strontium, and barium. Notice that those are all the exceptions in this section here. These end up being the cations for our strong bases. So when we look in chapter 8 for the acid-base section, those will be familiar. So I'm just giving you this little visual on the periodic table for this little shape. Okay, now I have another question for you. What about H2CO3? What is that? Okay, so we go through our solubility rules and we get all the way down to carbonate right here. But is this an ionic compound? So if we get to carbonate, then we're going to think, okay, this is solid. What kind of a compound is that?
The baking soda, like.
Baking soda is NaHCO3.
Oh.
So this is sodium, and then we're going to name the HCO3 minus, that is hydrogen carbonate. What is it when it's all H's there? Is it a metal and a non-metal? This is an acid. This is carbonic acid. Do you remember we did our acid naming? So we're reaching back to the acid naming. So before we even start on the solubility rules, we have to know this is an acid. This is carbonic acid. It's so important. It's in the sodas, right? It's in our soda water. It's in the ocean. It leads to ocean acidification, absorbing the carbon dioxide. It's so important. So all acids are aqueous. If you get to that rule, it's not correct. It's not even on the solubility rules because it's not an ionic compound. This is an acid, and all acids are aqueous. Okay, I like to add that one in because otherwise you don't notice. Like we just think it's going to be a solid, but it's not a solid. Okay, so this is the basis of precipitation reactions, is forming a new solid, and then it doesn't react any further. So it essentially pulls the reaction to the right. So it gives us something that drives the reaction forward to products. So here we have something that's clear and yellow, and something that's clear and colorless, and together they form a new red solid that precipitate, the iron 3 hydroxide. We are going to form new products. The only way we can form 2 new products by switching the cations. So this is a double replacement or double displacement, forming a new solid. So precipitation reaction has a new solid. Then we have to decide, after we predict our products, we have to decide, is it solid or aqueous? Now, one thing to keep in mind is that for something like iron, where it could be a +2 or a +3, it's going to stay the same. So in this case, we have Fe3 plus here. It's going to stay Fe3 plus here. And that is true for a double replacement reaction or double displacement. Okay, so compounds are neutral. They don't have any charges inside them. So let's write a new line so we can keep track of our charges. What's the charge on sulfate? What's the charge on magnesium? Maybe you know that one. Magnesium is in group 2, so sulfate must be 2-. All right, sodium is in group 1. Hydroxides are 1-. So we need to make a new compound with these 2 things and a new compound with these 2 things. So I'm going to write my new compounds. They have to be neutral. So make sure that you have neutral compounds. And then we're going to look at the solubility rules. We get all the way to rule number 10. There's no exceptions, so this is a solid. Rule number 1 says that this one is aqueous, and then we have to balance it. Okay, so predict your products making neutral compounds. Then we have to look at the solubility rules and decide, is it solid or aqueous for each one?
Number 1, balancing.
Oh, did I make a mistake? I did make a mistake. Thank you.
Yeah. Okay.
There we go. Okay, so it's just 2 sodium hydroxide. Yeah, I got the magnesium wrong. All right, on number 2, we should find that one is a solid and one is aqueous. All nitrates are aqueous. So it is a precipitation reaction. And then we need to balance. In number 3, I use the crossover method to write my neutral compound. Oh, I forgot to do my designations. Here we go. Okay, so you have to have those neutral compounds first, and that tells us what the subscripts have to be. Once we know the compounds, then we can make the number of atoms on each side the same by using coefficients in front of the compounds. And then our last step is to balance. So what we've written here are molecular equations. We've written all of our ionic compounds as neutral formula units, as if they were molecules. So we're looking for that neutral, smallest ratio of atoms that is neutral. But for ionic compounds that are aqueous, we know they float around independently. So we're going to write our ionic equation where we show all of our soluble ionic compounds as individual ions. Now the solids, liquids, and gases stay together as compounds. They don't dissolve. They don't break apart the way ions do. So we're really going to make that difference in the ions. Then we're going to cancel out anything that appears on both sides of the equation exactly the same way, just like we would in algebra. Just cancel out the things that are the same on both sides. That will leave us the net ionic equation, and that shows the driving force for the reaction, the thing that pulls it forward to products. Okay, so we're going to predict our products, assign solid, liquid, aqueous, but we'll balance it. Then we'll write all of our soluble ionic compounds as individual ions. Then we'll cancel out our spectator ions. They just kind of sit there watching. They never participate. And then we'll find our net ionic equation. Now, if everything cancels out in the net ionic equation, then there's no reaction. So we'll take a look at why that is, what that means. So here is one of our reactions from before. Let's go ahead and balance it. I like to line up the arrows because it just makes it easier to see. And we can use these beakers to think about what's in solution. So when I show sodium sulfate, aqueous, what does that look like in solution? All of those ions move independently. So I'm going to write that up here. All right, then I'll look at silver nitrate. And just to make it clear, I'm going to put 2 of them from the balanced equation. And that is everything on the reactant side. Now we'll do the product side. Okay, so what happens, these silver come together with that sulfate and they form Ag2SO4 solid. And what's left in solution? Now this one is a solid, it stays together. So when we look for the spectator ions, we're looking for things that are exactly the same. The sulfate was aqueous on one side by itself, and it formed a new compound on the right side, so it's not the same. The ones that are the same are the sodium is exactly the same on both sides, and the nitrate is exactly the same on both sides. So at the bottom we see the things that don't cancel. The net ionic equation, that shows us the driving force. So those silver ions collide with the sulfate and they stay together. They form a new solid and they don't dissolve again. So that's what gives us that arrow towards the solid. It pulls it out of solution. So let's do C. Okay, so we want to predict the products. So we form our neutral products, we'll get some balancing coefficients. And now we're going to write that total ionic equation. Oh yeah, okay, so sodiums are aqueous, potassiums are aqueous. So we'll break those all apart. Okay, did anybody write something like this? Or another way to ask that, why does that 2 come out in front? Is that clear? Does that make sense? So when we have this compound, they come apart. Those sodium ions come apart, and they function independently. There's no diatomic sodium, right? They're not connected together. There's 2 different sodiums, and they can move independently. So that's why that subscript becomes the superscript. Okay, so I'm going to write my products in here too. Now make sure that your charges are always balanced, so that the total charge on the reactants equals the total charge on the product side. Now, as we look at the spectator ions, right, I see the potassium is exactly the same on both sides. Carbonate, exactly the same on both sides. Same with the sodium, and same with the nitrates. So there's nothing that changes anything. So this is no reaction. They just get together and they have collisions. They bump into each other. I call it the party, right? They're just in there just bumping and watching and waiting for something to happen. But there's no show. There's no collisions that make a new substance, right? There's nobody getting together and going home. It's just, they're all just milling about having collisions. They're all spectators. So that's why there's no reaction if everything cancels out. In a precipitation, the driving force is going to be the formation of that new solid. Okay, so let's do this one. We'll start with balancing. So you have to find the charge on the nickel. And we get our new solid. And then what's left? Oh, I messed up my balancing. Yeah, we need 6 of these and 3 of those. There we go.
Yes.
So lithium plus, lithium plus. Right, we have, when this part breaks apart, we have 6 lithium plus. And then 3 chromates. So that gets back to that same question why didn't we write that sodium 2 plus? They act independently. So all 6 of those lithiums can move around without each other. They're just independent.
Why 6 lithium?
Well, each formula unit has 2, and there's 3 formula units in order to make our compound, our product. Okay, now we're going to cancel out everything that's the same on both sides. So lithium looks the same. Chloride looks the same, and our final equation shows the 3 chromates coming together with 2 nickel 3 ions to form our new solid. And that's what's driving the reaction forward. It's that formation of new solid. Because right now is the perfect time to do the lab for chemical reactions, where you'll send in your pages. So you're going to do it on paper or in your notebook. If your notebook is nice and neat and looks like the pages, you can do it in your notebook, or you can print out the lab manual pages and work on there.